Um, there are about 10 common shapes available on the market. There are, of course, more, but these 10 are the most common ones. And I know that when we get a request for an insert, in most cases, the customer already has defined the insert design, and he already has defined the insert dimensions, and it's mostly about selecting the right chip breaker and grade. But let's assume that you now have to make a decision based on a white sheet. There is a customer that has a lathe and he wants to turn some products without knowing anything about. So he doesn't have a tool, he doesn't have the insert, he's just going from a blank position. Of course, then you would look into things like, okay, what is going to use that specific insert for? Is it going to be for roughing? Is it going to be semi-finishing, roughing in combination with roughing, or semi-finishing, roughing in combination with finishing? Is he going to do straight turning or profile turning or face turning? Or does he want to have more versatility in that case? Is it a light duty lathe machine? Is the workpiece kind of tricky to machine because it could easily vibrate? Is it hardened material? Do we have an occurrence of interrupted cut? These are all kind of things that you need to take in consideration, or at least, let me put it like that, a customer has to take that in consideration. And as we serve the customer, we have to take that in consideration. Now, in principle, you could say that the shape will give you, let's say, a lead into to the operation that you can do with that shape. So the shape itself has some influence on that. Of course, there are more. The grade is important, the chip breaker is important, the nose radius, and so on and so on. But for now, let's look at the basic principle of the shape. You could basically say we have, with the 10 shapes, we have the V shapes. That is a very common shape. That is the most ideal grade shape of an insert when it comes down to profile turning. Why? Because there is only a 35, or enlarge this a little bit, there's only a 35-degree nose angle. So there is a good accessibility to a workpiece. And thus it can be used very ideally for profiling and resulting into, well, it also can withstand fewer vibrations, but it also generates fewer vibrations because the force that is directed into the workpiece by this kind of shape is lower than it would be by, for example, an S shape, the square shape version. Looking at the square shape version, I'm just jumping from left to right. Looking at the square shape version, this is the ultimate, let's say, on the other side. It's a typically an insert that is suited for roughing operation. This is where you're going to use that insert for straight turning, face turning, these kind of operations. You will never ever going to do any profile turning with this kind of insert, not this kind of shape. But it, because of the big nose angle, which is 90 degrees, it's ideally for hardened materials, interrupted cuts, and such. So then we have, I would say, probably the most versatile and universal type of shape, which is the 55 degrees nose angle, the shape D or shape K, which is, as you can see here, it's an ideal insert shape because the insert shape at itself can be used for semi-finishing, roughing, finishing, straight turning, profile turning, really versatile turning. It is also still ideal to be used on light duty machines, vibration sensitive workpiece, and so on. And then we have the most common one. Everybody that is being asked about to name an ISO code or an ANSI code for an insert will immediately say CNMG 432EN, and so on. It's the most common one. It also is an insert that can be used for interrupted cuts. As you can see here, it says it's not suited, or let me put it like it's suited but not the best choice for interrupted cut. But if you use the obtuse angle with certain tools, we will come to the tools next week. When you use them in certain roughing tools, and you use them with the obtuse angle of 100 degrees, it actually is better suited for interrupted cuts than the S group. And then we have the R, which is the round version, the round insert, the button insert, and these are predominantly for roughing operations, harness materials, interrupted cuts, and so on. And then we have the oops, mistake. We'll go back, up. Yes. And then we have the trigon shape and the triangle shape inserts, which have 3 cutting edges, in which the trigon shape with the 80 degrees is actually more or less equivalent when it comes down to semi-roughing capabilities to the C shape, which has also an 80 degree nose angle. So that's with regards to the shape. Moving on, the second thing is, okay, what's the difference between a positive and negative insert? Terminology often used. Basically, you can say that when it comes down to cutting, any cutting tool, in order to cut, it needs to have a rake angle. So you need to have the angle that cuts into the material, but it also needs to have a certain relief angle, as you can see here. Without a relief angle, no cutting will take place. You need to have that wedge pushing into the material. Now that rake angle with a negative insert, looking at the insert itself doesn't have that clearance built in. The clearance has to come from tilting the insert inside the tool in a negatively way. That's why the name is used, negative inserts. The big advantage, obviously, of this kind of insert is that it can be used on 2 sides. It doesn't necessarily mean that it is always the case, but it can be used on 2 sides. And then, of course, we have the positive inserts. And the positive inserts, they have the clearance built into the design. Very favorably used on light duty machines, or when you do finishing operations, these kind of where you have light cuts. It's an ideal insert, often used in that way, but you can only use it on 1 side, so potentially it's a more expensive insert than a negative insert, and thus the negative insert is mostly used for economic reasons as well. Most common relief angles are the 5, the 7, and the 11 relief angles, clearance angles, so B, C, and P. For the rest, note to be that remark needs to be made that there is a clearance angle called O. Okay, I don't know why it does that, but my mistake probably. Yes, there is a clearance angle O, and that clearance angle is reserved for the manufacturer to decide when he has, let's say, some clearance angle that is not in the ISO standard prescribed. So, for example, a 22 degrees angle would turn out to be O, and then the 22 degree angle would be noted somewhere else in the code or in the product description. So the third part of the design, that is the part, the letter that indicates the tolerance class. And why is the tolerance class so important? You have to see it like this. Indexable inserts, once a cutting edge is used, after the cutting edge is worn, you can basically unscrew the insert, turn the insert in the tool, and index it in that way. That's why the name indexable comes from. Now, when you start to index a tool, you lose your accuracy, because you need to really be aware that from a production point of view, that the tool, and looking at the main sizes, the main dimensions of the insert, being the inscribed circle, the thickness of the insert, and the tangent from the inscribed circle to the nose radius. All these sizes, they have some kind of tolerance in them from a manufacturing point of view. But when they have the tolerance in them from the manufacturing point of view, when you start using them in a tool and you start indexing them, every time you index, you have to be aware that you lose your offset values in your lathe. So you need to again measure the tool and the insert as a total before you start and continue your production. Now, the more accurate the tolerance class, the less time you will lose measuring, basically. So in the end, it comes down to having the best tolerance class, saving money in terms of time, basically. The most common tolerance class is the M tolerance class, which is a die press tolerance class. As you can see here, this tolerance is quite wide. And I believe that we are actually pretty good in our tolerance class. When you look here, the tolerance range from 0.08. This is, by the way, millimeters for the NAFTA people. There is a chart also in inch. But going from 0.08 to 0.18, the tolerance class is pretty good in our case. But nevertheless, it's there. Of course, more accurate ones are the G tolerance, which is a grinded tolerance, quite often used on positive inserts for finishing and this kind of operation. And we got the U tolerance, which is actually for low cost inserts, quite often used. Obviously, the production process doesn't need to be that accurate, so you can save money on that part. But on the other hand, you lose money as a customer when you start using these kind of inserts, because you basically have to spend more time in presetting your tools. So the last letter in the design to clarify is the one that is with regards to the types. And why do we have to consider the different types of insert? Basically, from a point of fixing, whether or not you have a hole or not, and if there is a hole, whether or not that hole has a partial countersink, and believe it or not, the angle of the countersink. If it turns out to be a single or a double-sided version, these are all variants that you could encounter when it comes down to the insert types. And then another thing which is embedded in the same code, in the same letter, that's the one that explains the rake surface, whether or not the insert has a chip breaker. And if there is a chip breaker, if the chip breaker is on one side or a double-sided version. Most common, our inserts are, like, say, in the first 3 rows, you will encounter the G, very often the M and the T. These are the 3 actually the main ones that we have in our range. When you are exchanging and running into exchanging an insert from a competitor, so cross-referencing with a competitor, be aware that when it comes down to the type of fixing, when the letter is any of the ones like W, T, Q, U, B, H, and so on, that you have to be aware of the countersink angle as well with regards to the screws. It's very important to realize that. And then there is also the possibility that there are special designs. And a special design basically means you are talking about a concept tool, concept insert. Exchangeability is going to be very difficult. That is indicated by the letter X. We don't have, as far as I know, we don't have turning inserts with an X. Might stand corrected, but I don't think so. But we do have milling inserts, ADMX, ADEX, and so on. These are the common ones that we have, that is really according to a special design, which with the ADMX and the ADEX is really the helical angle of the cutting edge, for those that know the ADMX, the milling cutter inserts. So that is about the insert types that you have to consider with regards to the design. Then I will go on to Ricky with regards to the dimensions.
Hi, good afternoon, everybody. I'm just going to take you through the main way we identify the dimensions and some of the differences between ISO and ANSI codes. So as Willem just went through, those first 4 letters are globally common to identify, the main dimensions. This is determined by ISO and ANSI. So depending on whether you're in a country that mainly uses metric system or imperial system. Now, although dimensionally some inserts can be the same, the ISO and the ANSI codes are different. Although, as I say, the insert in the box is the same. So the following digits from the 4 letters are the ones that identify the size. So if we look at the first two digits, or single digit in this instance, with regards to ANSI, this is the cutting edge length or size of the insert, which is determined by the size of the inscribed circle. So this is the main dimension that's used to indicate the size of the insert. And this can be different depending on the shape of insert that you have. So for instance, for equilateral shapes with cutting edges that have the same equal lengths, such as the V style and T style and D style, this differs between those, and obviously for round inserts. So round inserts, the inscribed circle is the full size. And then also non-equilateral shapes, so like the K and the L style, where they have cutting edges different lengths. The inscribed circle changes there as well, the size changes. If we look at ANSI, for instance, so for an ANSI designation in countries that use the imperial system, the value of the inscribed circle is the dimension calculated in 1/8 of an inch. So for example, an insert shape with an inscribed circle measuring 1/4 of an inch, the designation would be 2, because there are 2 times 1/8 in 1/4 of an inch. So that's where the number 2 comes from. In the top right hand corner here, our example has a number 4. CNMG 4, that would be 4 times 1/8, meaning the inscribed circle would be 1/2 inch. So that's how the ANSI code works. If the inscribed circle is not a whole number, then the designation is given to 1 decimal place. So for example, in the 532 instance, if we take 530 seconds as in 1/8, it would equal 1.25 times 1/8. So therefore, because we only use two letters, the designation would be 1.2. We would round it down from 1.25. So that's where that designation comes from. For ISO designation in countries using the metric system, the first 2 numbers describe the cutting edge length, and it disregards any decimals. So to determine the size of an insert, it's sometimes easier to measure the inscribed circle instead of trying to measure the cutting edge. So then you can follow the ISO table to work out the cutting edge length. So if we, for example, for a D-shaped insert shown like this, if you measure the inscribed circle 9.53 or 9.525, then refer to the table, you'll see that would be a D-style size 11, a size 11 insert. So that's sometimes an easier way of measuring the inserts. Where the edge length is lower than 10, we still keep with two letters, and we put a 0 in the front. So for instance, for a WNMG 08 insert with an 8mm cutting edge, it would be 008 in the code. In the case of non-equilateral shapes inserts, both ISO and ANSI generally use the value of the longest edge. So whatever the longest cutting edge is, either in millimeters or the length measured in quarters of an inch. Okay, so that's how we denote the size. If we look at how to understand the insert thickness, then, the next two digits in the code, or the next digit on the ANSI example, this denotes the thickness. If we look at the ANSI standard, the designation for thickness is the distance measured in 1/16 this time. So for example, an insert with a thickness of 1/8 would be designated as a number 2 because there are 2/16 in 1/8. So that's how that works. Again, if the thickness cannot be described in 1/16, the designation is given to 1 decimal place. So for example, again, a thickness of 5/64 would be 1.25 times 1/16, and therefore the designation, as previously, is reduced down to 1.2. According to the ISO standard, we would generally take the numerical value of the thickness in millimeters as the designation, and disregard any decimals. So if the resulting if the resulting designation has only 1 digit, it's preceded by a 0. So to give an example of that, an insert thickness of 6.35 would be indicated by 0.6. Also, just to bear in mind, you will see designations with a T, for example, T1. And this is because the 0.1 designation has already been used for an insert with a thickness between 1 and 2 millimeters. So, for example, an insert with a thickness of 1.59 is designated as 0.1 to the rounded down. Now, if we've got an insert with a thickness of 1.98, we can't use the 0.1 because that would confuse matters. Therefore, then we use the designation as T1. So similarly, an insert with a thickness of 3.18 is designated 0.3, and therefore the 3.97 would be designated T3. And that's why we have different O1 and T designations. The measurement method, so there are different ways to measure thickness that you need to be aware of. Generally, I mean, for flat top inserts, it's very easy to put a vernier across the insert to measure the thickness. But you need to be a little bit more careful when there are chip breakers involved. So, for instance, on a single-sided insert with chip breakers, you measure the cutting edge to the bottom of the insert, and that would give you the thickness. And it's a little bit more tricky on the double-sided inserts with chip breakers either side, whereby it's from the cutting edge to the lower edge, the base of the insert, if you like. So it does become a little bit tricky to measure that thickness. Okay. So moving on to the next letters in the code, and this is about nose radius of the insert. So for the ISO designation, again, this is a numerical value of the radius measured in millimeters. Again, we disregard any decimal point. So for an example, an insert with a nose radius of 0.4 is simply indicated 0.4. Similarly, an insert with a nose radius of 1.2 would be 12, would be indicated as 12. The ANSI designation follows a similar theme to the previous thicknesses, but this time the value is measured in 1/16 of an inch. So for an example, an insert with a nose radius of 132 would be indicated as a number 2 because there are 2/64 in 1/32. So that's how that works. A little bit different in the case of round inserts, where round inserts don't have a nose radius as such. generally the metric sizes, the two figures, the two digits for the nose radius are replaced by the designation MO, and those that have been converted from an inch value are normally indicated by 00. So that's basically the difference, just to give you an idea of the difference between ISO and ANSI codes on insert sizes. Okay, I'll hand you back to Christian.
Yes. So when it comes to the insert geometry, so this is the last two letters in the code, which belongs to the producers of the insert. Here is important to say that this position 9 and 8 are up to the manufacturers to show them or not, because the point here is that these two letters are already explained in the chip breaker. So this is really up to the producer or to the supplier of the insert if they show them or not. If they show them, we are talking here about the 8 letter. This is the edge preparation. So when we show the edge preparation, you can see here the basic difference in the edge preparation is that a sharp cutting edge is indicated by the letter F, which means in example used for aluminium, so really a sharp geometry. Rounded cutting edges are indicated by the letter E, which are normally the most common applied edge preparation in the market. Then we have also some special letters or edge preparation, which are normally not shown in the letter of the code. This is more included into the chip breaker. If we have a double chamfered cutting edge, so this is indicated by the letter T. And if this chamfered cutting edge is also combined with a radius, then it's designated with the letter S. If there is a double chamfered cutting edge, this will be indicated with the letter K. And if this double chamfered cutting edge is also included with some rounding, then it's indicated with letter B. So these 4 letters is more or less always included in the, with some exceptions of course, but it's more or less included in the chip breaker. There is one special design, it's called the wiper design. So when turning a workpiece, normally regular scallops will remain on the machine surface. This is a result of the combination of feet and the nose radius of the insert. So different radius along the big radius on the cutting edge will allow or produce a better surface, and this will give a higher surface finish on the turning part. But this wiper design will come up later on in the next one of the next presentations. We will go more deeper in this design. The 9th position is regarding the direction of the feet. So here it's also important that we can say basically all symmetrical designed inserts can use in both directions. So they are also indicated with the letter N if they are held in the correct tool. The exception, if there is, and this is also normally not mentioned in, sometimes not mentioned in the code of the producer or supplier of the insert. Different is it if you have the letter R, so this is suited for right-hand cutting, or if you have the letter L, so this is suited for the left-hand cutting. So I will hand over again to Willem.
Good. Zooming in a little bit on the chip breakers, we will at one point in time go and look at all the features and benefits of each chip breaker. For now, it's just an introduction into the phenomenon of a chip breaker and why they are there. Well, basically, up till this point, the insert is as standard as it can be, equal for any supplier. The differences is really made with that chip breaker design, and later on with the grade, which Ricky will explain. In our technical session of our catalogs, there you will find information about the chip breaker, about its application range, and the suitability with regards to work material. Now this one is taken from the old catalog, but in all honesty, it doesn't change that much. And probably in the next catalog, it will be changed also a little bit again to different styles. But the general idea, the purpose of it is that you will find in the technical section a drawing of the, just enlarge it a little bit, a drawing of the geometry, basic geometry, telling a little bit.
Technology training today.
Why?
Somebody can mute himself, maybe?
Oh. Me and Vicky have just got to go in the background.
It's not a tick box exercise, is it?
So I muted everybody. I hope I can still be heard. So we have the drawing, a line drawing of the geometry, which indicates the width of the T-land, the angle. We will come into that kind of details when we are really going to discuss the chip breakers in one of the upcoming trainings. But you will find the information there. And actually, if you are in need to compare something with a competitor, you will find that most of our competitors also have these line drawings. So you can actually already look a little bit like, okay, what is their geometry like? And then you can already make some rough comparison about the different chip breakers. Important is that in that same section, you will find an indication with regards to the suitability on the work material group, whether or not it's steel or hardened steel, stainless steel, cast iron, and so on. That indication is given by a full black box, which is basically the first choice. So it will be the first choice for that kind of material point. And if it's a half one, like you see here, and a half square one, it's suited. It's not your best choice. The best choice is probably to go for an insert that has a full black square when you're looking for an insert for cast iron. But nevertheless, this one can be used in that area. The last one is the open box, which actually was one that offered the possibility to look at it from a conditional provisional suitability. Now that box will change in the next catalog, so I will not go into the details there. It also gives an indication on the application range. Now you see here the letters R, M, and F. This is basically a rough indication to say we are talking here about, with the R, about roughing operations, so heavy cuts in terms of feet, larger feet, and higher depths of cut, and yeah, that's it basically. We have the M, which is the semi-finishing or medium turning operations, and we have the F, which is the finishing operations, the smaller cuts. So if you would make a line drawing, this area here would be finishing. A bigger area like this would be something like medium, and then the biggest one on top would be the really roughing, or actually we also have SR, serious roughing. It's really the heavy indications. Now, when we talk about a chip breaker, it's really important to realize that the name chip breaker is actually also describing its purpose. Its purpose is to form the chip when it's cutting the chip, to form the chip like this, and to make sure that the chip starts to break. That's its whole purpose. That's the point of a chip breaker. The limitation of it is that chip breaking will normally only occur in a specific area with a specific feed and a specific depth of cut. When you go outside the limits, the boundaries of that turning area, application area, you will encounter difficulties in breaking the chips in a correctly way. So basically, whether or not you move and feed the tool and the insert too slow, or you have a too low depth of cut, you will encounter a situation where the chips get long and stringy. You don't break the chips anymore, which is a potential danger because the chips will will spiral itself around the bar, the workpiece, and it will potentially break the tool and could actually be quite damaging and harmful for the operator itself as well. On the other side, if you go and you overfeed the tool and the insert by applying too much feed, or even combination with too much depth of cut, then you risk, of course, clearly a breakage of the insert, which is also potentially very dangerous. So in all cases, my remark now at this stage, and we will go into the cutting conditions later on, but in this stage, I would say if you are going to apply any tool, insert or milling cutter, by the way, but insert in this case for turning as well, look at this table inside the technical section and start with your values or your recommendations to the customer on the middle point of the application area. In this case, a 1 millimeter depth of cut with a feed of 0.25 as a starting point would be very nice. And then you can move on. When you start to encounter the boundaries, you will see that you will get into situations where you need to be really cautious, and when you go over it, of course, as I said, you risk breaking. So that's what, with regards, very briefly, with regards to the chip breakers. So Ricky, can you wrap it up with the grades?
Yeah, sure. Okay, so just to give you an update on the grade. So the last set of digits in our code indicates the grade. And when we say grade, we term that as a combination of the cutting material and the coating together. There is an ISO grade classification system, and this is a reference to carbide substrates and enables all end users and manufacturers to make an easy comparison between them. So this coding system, which is shown at the top there, is a letter and 2 numbers. The letter indicates the workpiece material for which the grade is primarily suited, so whether it be steel, stainless steel, cast iron. And then the number is an indicator of suitability for the level of machining. So for instance, a low number like 0.5 would imply a low toughness, quite a high hardness, so for light feeds and high speeds. And opposite to that, a high number would imply a high toughness and a low hardness for heavier feeds and lower speeds. So that's the ISO classification. Now, when it comes to our inserts, the Dormer Pramet grade code, we start with a letter followed by 4 digits. The letter stands for the primary application. So, for example, T stands for turning, M stands for milling, and D stands for drilling, and so on. And then if we look into the digits, the first digit after the letter, this indicates again the main work material and coating method. So, for instance, if we look at 4 and 5, these are primary for K group materials, so cast irons. The 4 would be a PVD coating, and the 5 would be a CVD coating. Similarly, we have a 6 and 7. These are primary for M group materials, and the 6 would be a PVD coating, and the 7 would be CVD. And then also we have 8 and 9. In our instance here, we show a 9. So these are universal grades for steels. Again, the 8 would be a PVD coating, and the 9 would be a CVD coating. So that's the first digit after the letter. The second digit indicates the generation. So the higher the number, the newer the grade. So T9325 is a fairly new grade. The next one will be T94 and so on. So that gives you an idea of how old the grade is. And then the final 2, the third and fourth digit, these combined follow the ISO classification. So in our instance here, 25 would be on the 25 scale of the ISO classification. So it gives you an idea of the hardness or toughness of the grade. So if we look at coatings, just to give you a bit of information about coatings, we generally divide them into two based on method of coating. So as I said earlier, CVD is a chemical vapor deposition, and these coatings are usually thicker, harder, and higher wear resistant, allowing quite high cutting speeds. And the opposite of that, PVD, physical vapor deposition. These coatings are much thinner and typically smoother, and better suited for machining at lower speeds. So it all depends on the machine and the application that you've got, depending on which type of coating you choose. In summary, with regards to grades, indexable inserts are most commonly manufactured with cemented carbides. Most of our grades are made from cemented carbides, which are basically particles of hard metal cemented together by a binding material. So this is why when you see HM, hard metal, generally the hard metal particles that we use are typically tungsten carbide, and the binding material is predominantly cobalt. There are many variants that can be made by changing the ingredients, the kinds of carbide powder, using different grain sizes, using different levels of cobalt to bind them together. So the result is a great number of possibilities, great number of substrates to choose from, and this is why that you will find so many different grades on the market. All competitors use different ingredients and different grades, striving to to have the best, most resistant grades. So that's a summary of our grades.